Today we are going to learn about mastering Kubernetes efficient resource management. We will explore how to configure and manage resource requests and limits efficiently, optimizing both application performance and cost in Kubernetes environments.
Welcome to our session on mastering Kubernetes efficient resource management. In this video, we'll guide you through the essential strategies and best practices for managing resources in Kubernetes. Resource management is crucial not only for optimizing application performance but also for ensuring cost efficiency within your Kubernetes environment. Throughout this video, we'll cover key concepts including resource requests and limits, CPU and memory configurations, and best practices for setting resource constraints. By the end of this session, you'll be equipped with the skills to configure and manage resource requests and limits effectively, monitor resource usage, and handle resource quotas and limits at the namespace level. To master resource management in Kubernetes, it's essential to understand the concepts of resource requests and limits. Resource requests are the minimum amount of CPU and memory that a container requires to run efficiently. These requests help the Kubernetes scheduler decide which node to place a pod on. On the other hand, resource limits specify the maximum amount of resources a container can use. Setting these limits prevents a container from consuming all available resources on a node, which can lead to resource contention and affect the performance of other running applications. Imagine a scenario where multiple applications are running on the same node. Without proper resource limits, one application could potentially monopolize CPU or memory resources, starving others. Therefore, setting accurate resource requests and limits is critical for maintaining balanced workloads and efficient application performance. In Kubernetes, these configurations are specified in the pod specification, using the resources field. For instance, you might set a request for 100 meters CPU and a limit of 200 meters CPU for a container. This configuration ensures that the application has enough resources to start with but doesn't overconsume beyond its defined limit. By understanding and implementing resource requests and limits, you're taking the first step towards efficient Kubernetes resource management.
Configuring CPU and memory resources in Kubernetes is a critical aspect of resource management. Proper configurations ensure that applications have the necessary resources to run smoothly without overwhelming the system. To configure CPU and memory resources, you need to define requests and limits in the pod's resource specification. CPU resources are measured in millicores, where 1000 meters equals 1 core. For instance, setting a CPU request of 500 meters means that the container requires half of the CPU core to run effectively. Similarly, memory is measured in bytes, with common units being MB for megabytes and GB for gigabytes. An accurate configuration of these resources can significantly impact the performance of your workloads. If requests are set too low, the application might not have enough resources to function, leading to poor performance. Conversely, setting limits too high might result in resource wastage, increasing costs unnecessarily. In practice, you should start by profiling your application to understand its resource consumption patterns. Tools like Kubernetes built-in metrics server or Prometheus can assist in gathering this data. Once you have a clear understanding of your application's resource needs, you can set appropriate requests and limits. In our demonstration today, we'll walk through configuring CPU and memory resources, showing you how to define these in your pod specifications and apply them effectively in your Kubernetes environment. When it comes to setting resource constraints in Kubernetes, following best practices is vital for maintaining an efficient and cost-effective environment. First, it's important to thoroughly understand your application's resource needs. This involves monitoring and profiling your applications to gather data on CPU and memory usage under various load conditions. By understanding these needs, you can set more accurate resource requests and limits, balancing performance and cost. It's crucial to avoid over-provisioning resources, as this can lead to increased costs without any performance benefit. Conversely, under-provisioning can cause performance degradation if the application doesn't have enough resources to operate effectively. Another best practice is to regularly review your configurations. Applications evolve over time, and so do their resource requirements. Regularly revisiting your resource configurations ensures that they remain aligned with the application's current needs. Additionally, leveraging Kubernetes tools like the horizontal pod autoscaler can help dynamically adjust resources based on real-time data, optimizing resource usage. Lastly, it's beneficial to use monitoring and alerting tools such as Prometheus and Grafana to maintain visibility over your resource allocations and usage, allowing you to respond promptly to any resource-related issues. By adhering to these best practices, you can achieve a more efficient Kubernetes environment, optimizing both performance and cost. Monitoring resource usage in Kubernetes is essential for maintaining a healthy and efficient environment. Effective monitoring allows you to identify resource bottlenecks, optimize performance, and prevent over-provisioning. Kubernetes offers several tools to assist with resource monitoring, the most notable being the Kubernetes metrics server. This lightweight tool provides resource usage metrics at the node and pod level, allowing you to gain insights into CPU and memory consumption. For more advanced monitoring, Prometheus is a powerful option. Prometheus is an open-source monitoring and alerting toolkit that collects and stores metrics as time series data. By integrating Prometheus with Grafana, you can create detailed dashboards that visualize resource usage across your Kubernetes clusters. These dashboards offer real-time insights and historical data, enabling you to track trends and make informed decisions. Setting up alerts for anomalies is another critical component of effective monitoring. By configuring alerts in Prometheus, you can receive notifications when resource usage exceeds predefined thresholds, allowing you to take immediate action to mitigate issues. Continuous improvement is key to optimizing resource management. Regularly review your monitoring data to identify patterns or trends that could indicate areas for improvement. By continuously refining your resource management strategies based on monitoring insights, you can maintain an efficient and cost-effective Kubernetes environment. Overcommitment in Kubernetes refers to the practice of scheduling more resources than are physically available on a node. While this can increase resource utilization and efficiency, it also carries the risk of resource contention, where multiple applications compete for limited resources. Resource contention can lead to degraded application performance and even cause some applications to crash if they can't access the resources they need. To manage overcommitment effectively, it's essential to implement strategies that prevent resource contention. One such strategy is to use Kubernetes Quality of Service (QoS) classes, which categorize pods into 3 classes: guaranteed, burstable, and best effort. Guaranteed pods have both CPU and memory requests equal to their limits, ensuring they receive the resources they need. Burstable pods have some, but not all, resource requests, allowing them to receive more resources when available. Best effort pods have no resource requests or limits set, making them the lowest priority in resource allocation. By classifying your pods appropriately, you can prioritize critical applications and reduce the risk of resource contention. Another strategy is to regularly monitor resource usage and adjust resource requests and limits based on the observed data. Practical examples include setting higher resource requests for critical applications and using monitoring tools to identify and address any contention issues promptly. By managing overcommitment effectively, you can maintain a balanced and efficient Kubernetes environment. Autoscaling is a powerful feature in Kubernetes that allows you to automatically adjust resource allocations based on real-time data. Kubernetes offers 2 types of autoscalers: the vertical pod autoscaler (VPA) and the horizontal pod autoscaler (HPA). The VPA adjusts the CPU and memory requests and limits of a pod based on its resource consumption. This is particularly useful for applications with varying resource requirements over time. By using VPA, you can ensure that your applications always have the right amount of resources, optimizing both performance and cost. On the other hand, the HPA adjusts the number of pod replicas based on metrics such as CPU utilization or custom metrics. This is ideal for applications with fluctuating workloads, allowing you to scale out to handle increased demand and scale back in during periods of low activity. While both autoscalers have their advantages, they serve different purposes and are used in different scenarios. For instance, VPA is beneficial for stateful applications where resource needs vary but the application doesn't scale horizontally. HPA is more suited for stateless applications where scaling out is feasible. Configuring these autoscalers in Kubernetes involves defining policies in your deployment specifications. By leveraging autoscalers, you can automate resource management, ensuring optimal resource utilization and application performance. In Kubernetes, resource quotas are used to control the amount of resources that can be consumed by applications within a namespace. This is particularly useful in multi-tenant environments where multiple teams or applications share the same Kubernetes cluster. By setting resource quotas, you can prevent any single namespace from consuming all available resources, ensuring fair resource distribution across the cluster. Resource quotas are configured at the namespace level and specify the maximum amount of CPU, memory, and other resources that can be used within that namespace. For example, you might set a CPU quota of 10 cores and a memory quota of 32 GB for a particular namespace. By doing so, you prevent applications in that namespace from exceeding these limits, reducing the risk of resource contention and overuse. Balancing resource allocation across namespaces ensures that all applications receive the resources they need to operate effectively. Configuration of resource quotas involves creating a resource quota object in Kubernetes and specifying the desired limits. It's important to regularly review and adjust these quotas based on the changing needs of your applications and teams. By effectively managing resource quotas and limits at the namespace level, you can maintain a balanced and efficient Kubernetes environment, optimizing resource utilization and cost.
To fully understand resource management in Kubernetes, let's explore some practical examples and strategies. Consider an e-commerce application with fluctuating traffic patterns. During peak shopping seasons, the demand on the application increases significantly, requiring additional resources to maintain performance. In this scenario, implementing resource requests and limits ensures that each component of the application has the necessary resources to operate effectively, even during high traffic periods. To handle the increased load, you can use the horizontal pod autoscaler to automatically scale out the number of application instances, ensuring that resources are allocated efficiently based on real-time demand. Additionally, setting appropriate resource quotas at the namespace level ensures that the e-commerce application doesn't consume more resources than allocated, preventing resource contention with other applications running in the cluster. Another practical example involves a data processing pipeline with varying resource requirements. By using the vertical pod autoscaler, you can automatically adjust CPU and memory requests and limits based on the pipeline's resource consumption, optimizing performance and cost. Continuous improvement is key to effective resource management. Regularly review your resource configurations, monitor resource usage, and adjust your strategies based on observed data and trends. By implementing these practical examples and strategies, you can achieve efficient resource management in your Kubernetes environment, optimizing both application performance and cost. In conclusion, mastering resource management in Kubernetes is essential for optimizing both application performance and cost efficiency. Throughout this video, we've explored key concepts such as resource requests and limits, CPU and memory configurations, best practices for setting resource constraints, and the importance of monitoring resource usage using Kubernetes tools. We've also discussed managing overcommitment and resource contention, using vertical and horizontal pod autoscalers, handling resource quotas and limits at the namespace level, and practical examples of resource management strategies. Remember, continuous monitoring and adjustment are vital for maintaining an efficient Kubernetes environment. By leveraging Kubernetes tools and applying the skills you've learned, you can achieve effective resource management, ensuring that your applications run smoothly and cost-effectively. Thank you for joining us on this journey to mastering Kubernetes resource management, and we encourage you to apply these strategies in your own environments.